Alright, so let's do a little bit of math with a mirror. First off, the object distance is s to the object in the mirror. The image distance is s prime. It's a spherical mirror, so the focus is half the distance between the center of the mirror and the actual vertex. We know this lens equation, which now we're calling the mirror equation for the mirrors. 1 over s plus 1 over s prime equals 1 over f. Now we need to put in positive and negative signs, so whenever a distance is where the light belongs, which in this case the object's on the left, so the light all belongs on the left of the mirror, then it's a positive value. If an object ever appears, or the distance ever measured from the right, then it's a negative value. So for this lens, you can see that the object is a positive distance, s prime is a positive distance, the focus is a positive distance, and so is the center. So for this setup, everything's positive in the numbers. The magnification is the image height over the object height, and that's equal to negative image distance over object distance. And that's important because the magnification can tell us a couple things. If the magnification is negative, it's an inverted image. If the magnification is positive, it's an erect or upright image. Also, if the magnification is greater than 1, it's large. If the magnification is less than 1, it's been reduced in size. In terms of the s's, if I have a positive s prime, that tells me that the image is in the real side where the light belongs. So it's a real image, I mean. And if it's a negative s prime, then the object appears, the image appears, I guess. The image appears where the light doesn't belong, and it's a virtual image. For a convex lens, it's the same thing, but a convex lens is convex mirror. It's the same thing, but a convex mirror is a negative mirror, so it's a negative focus, negative center, and in this case, a negative distance to the image. Equations, they're all going to be the same, and they tell us the same thing we did before, so we're still going to look at for the magnification, same formulas, and the distances. They all mean the same thing. So that's all the same. Let's look at an example problem. So here's a large Christmas ornament. So here's the very first selfie. A large Christmas ornament. The glass ornament in the back of my room has a diameter of 0.75 feet. My head has a height of 2/3 of a foot. By the way, I don't know if my head's really 2/3 of a foot, but whatever. And is 4 feet in front of the ball surface. So here's a couple questions. What kind of mirror is this? How far away is the image from the surface? Is the image real or virtual? Prove it. Is the image upright or upside down? Okay, first off, type of mirror. So this is a convex mirror. So in other words, if I had a ball, this is the outside shiny part of the ball reflecting back. How far away is the image from the surface? Well, to find this, I'm going to need to use my equations. So in terms of my givens, I know the distance, I know the object height, I know s, the distance between the object and the mirror, that's 4 feet. The radius is negative 0.7375, and the focus is half the radius. So that's 0.1875 feet, and s prime is what I'm after. So I'm going to use my mirror equation. 1 over f is equal to 1 over s plus 1 over s prime. Putting in my numbers, making sure I have my negative signs, and I get that s prime, or 1 over s prime, is equal to negative 5.583 repeating to find s prime. That gives me basically negative 0.18 feet behind the mirror. The image is virtual because it's negative. I also know it's virtual because all convex mirrors give you virtual images. Is the image upright or upside down? Well, magnification can determine this. So the magnification is the image height over the object height, or negative image distance over object distance. So I'm going to use the distances. So negative of a negative 0.179 feet divided by 4 feet. So notice it was a negative in front of the formula, and the formula had a negative sign in front of it. The two combined give me positive 0.044 for the magnification. So it's smaller than the original, and because the magnification is positive, I know that it's upright. But I knew it was going to be upright anyways because it was a convex mirror, and that's what I expect. All convex mirrors give you images that are equal to or less than the original, and they're upright.